So, welcome to proof 2.3. This proof is basically all about using the moment generating function of a normal distribution to explore some of its properties. So, let's see. So, a moment generating normal distribution rather is defined by its PDF, and its PDF is the following function. 1 over sigma root 2 pi times e to the minus x minus mu squared over 2 sigma squared. So that is the density function of the normal distribution, and we are given its MGF, its moment generating function. We're told that, so we don't have to compute this ourselves. We are told that that is e, so I'm just going to write it out with this notation. Exponential function just means e to the mu t plus sigma squared t squared over 2. Right. So what do we need to do? So the first part of this proof asks us to show that the expected value of, and we're going to say that that x is a random variable that is normally distributed. And we want to show that the expected value of x is in fact mu. Well, how do we do that? Well, the expected value of x is its first moment, and we know that to find a moment using the moment generating function, to find the first moment, we take the first derivative and evaluate it at 0. So first take the first derivative of the moment generating function. I'm gonna switch colors here. And what's that equal to? Well, that's going to be, so when you take, so it's going to be e to the everything that's right up here, t squared over 2. But we need to use our chain rule, so all of that gets then multiplied by mu t, oh, oops, I forgot. That's important. The addition symbol there. Mu t plus, oh wow. Actually, I'm just going to rewrite that because I forgot several things. So that was just supposed to be basically everything that's up here. T squared over 2. Okay, now we'll use the chain rule. So that's mu plus okay, so sigma squared over 2 times 2 is just sigma squared, and then t. Finally got that right. Okay, well then sigma, this evaluated at 0 is the first moment, which we're trying to find. So what's that going to be? Well, this portion of it, what's that going to be? Well, substitute 0 in for the t, all of this just goes to 0, so that's e to the 0, and e to the 0 is anything to the 0th power is just 1, so then we're multiplying 1 times this. Well, substitute 0 in here, we're just left with mu, so we have in fact shown that the expected value of x is mu. For a normal random variable x. So, next part of the proof asks us to demonstrate that the variance of our normal random variable x is equal to sigma squared. Well, we know that one way to calculate variance is the second moment subtract the square of the first moment. And we know that this, well, we just calculated the first moment. We said that we demonstrated that it's mu, so this is mu squared. So now we are going to calculate the second moment and then come back to this afterwards. So we'll do that with our moment generating function as well. So recall that we already calculated the first derivative. And I'm just going to copy that here. Maybe I can find a tool to do that. That looks promising. Okay. So I just want to copy that, paste, and move this down here. Okay, I'm just going to set that on top there. Okay, that was a little bit messy, but oh, what now? Okay, so this video is going to need some edits. C'est la vie. Okay, is equal to mu plus sigma squared times t all times e to the mu t squared plus sigma squared t squared over 2. So we now calculate the second derivative of the moment generating function. We just use our product rule, so that is going to be sigma squared times e to all of this mu t squared plus sigma squared t squared over 2 plus mu plus sigma squared t times the derivative of this term, but we just barely, but we know what that is. We know that's just another one of these guys. So we end up with that squared times all of this stuff again. Right. And now, in order to get our second moment, which is what we're calculating right now, remember, we have to set this t equal to 0. So what does that leave us with? Well, all of this stuff goes to 0, so this is just sigma squared times 1, this term, so that's just sigma squared. And then this term, to evaluate that, we notice that, well, again, all of this is 0, so this is just e to the 0, 1. So 1 times whatever this is, so mu plus 0 squared, so that's just mu squared. So recall that we are calculating the variance of x, and we already so we're getting this for this term, so sigma squared plus mu squared for the first term that we used to calculate the variance. But then we still need to subtract the square of the expected value of x, but we already figured this out. That's mu squared, so mu squared subtract mu squared is 0, and that leaves us with just sigma squared, as we wanted to show. So there's one more part to this proof. We are asked to show that for two random variables, two normally distributed random variables, x1 and x2, where x1 has a mean of mu1 and the variance of sigma 2 squared, and x2 is also normally distributed with a mean of mu2 and the variance of, that should be a 1, not 2, and a variance of sigma 2 squared. And these are independent, that's important, independent random variables. We want to show that all of that we just wrote implies that the random variable x1 plus x2 is also a normal random variable and one that has mean mu1 plus mu2 and variance sigma 1 squared, so the variance of our first variable, random variable, plus the variance of our second random variable. Well, we recall that for independent random variables, the moment generating function of their sum is equal to the product of their respective moment generating functions. So it's important to remember that because we know that they're independent. Okay, well, we know that this guy is, in fact, e to the mu1 times t plus sigma 1 squared over 2 and this guy is e to the same thing but with different mu's and different sigmas. So all of that is equal to e to the mu1 plus mu2 times t plus, oh, both of these, I forgot a t squared there in the numerator. So plus sigma 1 squared plus sigma 2 squared t squared over 2. And we notice that this is in fact the moment generating function of a random variable that's normally distributed with mean mu1 plus mu2 and variance sigma 1 squared plus sigma 2 squared. And in fact, we know that any moment generating function that is this is the moment generating function of a random variable with this distribution. So we have proved what we set out to show.